the afternoon talk. We're going to have Jean-Pierre talking about from dynamics to geometry and free-by-cyclic groups.
All right. Thank you to the organizers for this great opportunity, and for the rest of you to coming to attend this mini course. So I want to tell you about something I'm fascinated about in geometric group theory, which is usually I think of as being at the intersection of various areas of math. So you can sort of like study dynamics and only do dynamics, or do algebra and only algebra, and geometry or only geometry. But I'm more interested in places where the things sort of intersect in between. And so those are very abstract words. So I'm going to do some specifications here. And when I say dynamics, you're going to see more details later. So this is just a very quick overview. I'm thinking about automorphisms of a finitely generated free group F. So automorphisms of free groups, I think of them dynamically because I can iterate them. And that's about it. So if I can iterate something, I think that as a dynamical system. Algebra here will be free-by-cyclic groups, which I'll define. But they're groups that are semi-direct products of the free group and the integers. So in the definition, you sort of have to decide, you need to pick an automorphism of a free group to actually make sense of this free-by-cyclic group. And then, so you can sort of study their algebraic properties, ask about their subgroups, things like that. And then geometry here, well, since this is geometric group theory, you pick a finite generating set and you consider the Cayley graph. Or generally geometric models that I'll define. And so one thing you can now ask about is, okay, there are geometric properties over here. Like if I have a graph, I can ask whether it's delta hyperbolic. And what does that tell me about the subgroups of the free-by-cyclic group? And if I know that, what does that tell me about the automorphism of the free group? And is there an equivalence between those three things? So here's a theorem of Brinkman from 2000. You can sort of be interested in delta hyperbolicity over here.
The red is very hard.
Oh, I thought it was supposed to be the. All right, this is theorem. There's nothing too important there. That's Brinkman, 2000. And great. Does it look like yellow or white to you? Yellow. It does? Okay. I do want it to be slightly different from white. So delta hyperbolicity over here, there's a theorem, maybe you can attribute it to Gromov, or a proposition that says if you're delta hyperbolic as a group, then you have an algebraic consequence here is you have no subgroups isomorphic to z squared. So you have this implication over here. And then one of the things that I'll give you as exercises for your discussion sessions is that if you have no z squared subgroups, that tells you that your automorphism has no periodic conjugacy classes. Again, I'll define these things more generally. And now the theorem of Brinkman, which is really where this comes into play, is that there is an implication that says if you have no periodic conjugacy classes, you're delta hyperbolic. And I think this theorem is very beautiful because now you have three invariants. One is a geometric invariant. This is an algebraic invariant, and this is an dynamical invariant property. And you're sort of saying all these three things are equivalent. And the whole point of this course will be statements like this, theorems where I relate dynamical properties to geometric properties and algebraic properties. Oh, wow. All right. So let's get started here. Dynamics. I have F is going to be a finitely generated free group. Finitely generated free group. If we do want to fix base, talk about basis, let's say it's generated with A1 to AR, R for rank. But I'll never really, for the most part, I won't really need to talk about this basis. So F is the automorphism group. Automorphism group. And then NF is going to be the inner automorphisms. So the automorphisms given by conjugation by elements in the free group. And then the point is that this is a normal subgroup, so I can look at the quotient subgroup. So out F N, which is odd F modulo the inner automorphisms, is the outer automorphism groups. Outer automorphism group. And this is the group we're interested in. So for us, inner automorphisms are going to be trivial things. Okay, so there is a, I want to think about this as a dynamical system. So we're going to see how some properties to think of, to consider. So properties of, this is a quotient group. So elements of this thing here are outer classes. So those are outer automorphisms, which are classes of automorphisms, right? So I'll typically use the notation square bracket phi when I'm thinking about the outer automorphism, and phi itself is the automorphism that represents the class. So we've chosen some outer automorphism. What are some properties you can ask about? You can talk about it being finite order. All right, so finite order, it is a group, so you can talk about finite order. And that means you can find a power where this thing is trivial. And if we really want to expand what that means, is there exists an n greater than or equal to 1, where phi to the n, so the representative I chose, some representative, doesn't matter which one, is an inner automorphism. Okay, so here an example. In rank 2, so let's say F it has basis A and B, then you can consider the automorphism that sends A to A and B to A, B, A inverse. So this is actually trivial. So you don't even need, like n can be equal to 1. In the outer automorphism group, this is a trivial element, even though it's not a trivial automorphism. More interestingly, if you consider the automorphism that sends A to B and B to B A inverse, you can show that the 6th power of this thing is an inner automorphism. So it takes quite a few iterates to do this. And then sort of like the negation of this will be infinite order. So I don't know, I'm not going to write what that means there. For all and da 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 da. no power is actually an inner automorphism. So it's the complete negation of being finite order. And some nice examples to keep in mind here are you send A to A and B to B A inverse. So I put this example here to say that they look quite similar. This has an A and this doesn't have an A. One is trivial, the other one is infinite order. And then another example which has infinite order is A goes to B, B goes to BA. Again, look quite similar. This is BA inverse, but this one is BA. But this one is infinite order. This one has order 6. So now the question you might be curious about is how do you tell which one is infinite order and how do you tell which one is finite order? Other properties that I'm now going to define today. Well, I'll define one because we've already seen its relation to the rest of the talk. So heteroidal. So these were the things I was defining. Heteroidal means for all n and all non-trivial elements, then phi to the n of A is not conjugate to A in F. So it's only, you're sort of saying you don't have any periodic, not any periodic elements, but really periodic conjugacy classes of elements under the action of the outer automorphism. In terms of conjugacy classes, you're saying phi to the n of A, the conjugacy class of this is not equal to the conjugacy class of A in F. So that's the definition of no periodic conjugacy classes, so heteroidal. I could have said that at that stage. And some other properties you will see by the end of this mini course, but not today: irreducible, and other properties, growth type. So you're going to have some automorphisms that grow polynomially, others that grow exponentially. This is an example of something that's growing linearly. This is an example of something that will be growing exponentially to be defined. All right, growth type. So what about this is dynamical? So dynamical invariance. I'm not crossing that out, I'm underlining it. Dynamical invariance, I'm making this notation up, so if you don't like it, choose your own. But our conjugate, like an outer automorphism phi and an outer automorphism psi, or maybe not psi, but phi as well, are going to be like dynamically equivalent if there exists an integers n and m greater than or equal to 1, such that the nth iterate of phi and the nth iterate of m are the same. Actually, not the same, but let's make it even slightly weaker. Conjugate in out of F. So you can find some element in out F that conjugates this power to this power. And then I'll say a property question mark is a dynamical invariant. Property X for now, let's say, is a dynamical invariant if you get the following implication. Phi being dynamically equivalent to phi is a var phi implies that one has property question mark if and only if the other has question mark. All right, so what does this really mean? If I wanted to say being finite order is a dynamical invariant, then I'm saying if you have two outer automorphisms and they're dynamically equivalent, then one being finite order implies the other one is. I'm stating this as an if and only if, but because of, if you actually wanted to prove something is a dynamical invariant, without loss of generality, it's enough to just prove one implication, right? Because the same argument will just give you the reverse implication. So it's a dynamical invariant because two dynamically equivalent outer automorphisms will share that property. All right, so now here's some exercises. So for the exercise session, I unfortunately did not prepare a PDF, so I'm going to be writing the exercises on here. And hopefully you're taking notes. So exercise 1, being infinite order or maybe finite order, it doesn't, they're equivalent things. I think I like finite order as a statement. Being finite order, atoroidal, and this year, it's not really an exercise because I haven't defined it for you yet. So growth type, you'll see this tomorrow when I define what growth type is, and then that will be an exercise as well. Are dynamical invariants. All right, again, I'm going to use EX for exercise, not example. Yeah, so being finite order, atoroidal, and growth type for now hasn't been defined yet. These are dynamical invariants. And can you see this, or do you want me to raise this? All right, so there's one missing thing that I underlined there that I've not stated as being a dynamical invariant, and that's being irreducible. So fact, being irreducible, which hasn't been defined yet, is not. And it will kind of boil down for one, you'll have things that are irreducible and finite order. But if you pass to a power, then you sort of have a power is going to be trivial, but the trivial automorphism is not irreducible. So that's kind of like going to be the prototypical simplest example of something that's irreducible and not. It's the finite order ones, but there are also infinite order examples. And then I'll state a theorem, which you can't appreciate for now, but maybe at the end of the course you will. It's by Dodal, Popovich, and Leininger. So it's not an old theorem. Atoroidal plus irreducible. So the composite property of being atoroidal and irreducible is a dynamical invariant. So you haven't seen the definition of irreducible yet, so maybe you can't appreciate it yet. Any questions? So that's a quick sort of how I think about things dynamically. So let's talk about to algebra. So that was dynamics. Let's move over to algebra. And so you're given the free group and it has some basis A1 to AR. I want to define a free-by-cyclic group for you. You also have an automorphism phi. So this is an honest automorphism, not an outer automorphism. And I'm going to construct G phi. Here's our presentation. Is going to have A1 all the way to AR, and then an extra generator T, sometimes called the stable letter. and it's T, A, and your relations, you're going to have R relation, one for each basis element. So T conjugates AI to its image under the automorphism phi. For I equals 1 all the way to R. So this is our presentation for G phi, and also denoted as free semi-direct Z, but with an implied automorphism that if you change the automorphism, you're changing the group. So if you want to, if I just write without the script, it's unclear what that free-by-cyclic group is. So now I've given you a process for given an automorphism of a free group, which I want to think of as a dynamical system. I can construct a group. It's free-by-cyclic, and also you can call it mapping torus. For those familiar with this story, or maybe with a similar story, there's sort of like an analogous thing that's actually the motivation for much of the theory, which is rather than study free group automorphism, you can study surface homeomorphisms. And you can form a mapping torus for a topological map. And you can add things relating dynamical properties of your homeomorphism to topological properties of your mapping torus. And later on, when you talk about geometry, there's something there as well. But I can't really talk about that motivation because I'll run out of time to even discuss the free group automorphisms. But you don't need to know that motivation to understand what's going on in the free group automorphism setting. But at least that's where the name mapping torus comes from that topological context. All right, so we have a group. So let's talk about some group invariants. What does it mean to be a group invariant? In general, you want to say, all right, I'll just say it in the context of free-by-cyclic groups, but this you can really talk about group invariants in general. And property question mark, all right, sorry. Before any of this makes sense, I need to make an observation. So new exercise. Wasn't part of my list, but I'll give it to you as an exercise here. If phi equals, okay, I'm going to use psi now. If phi equals psi in the other automorphism group, then G phi is isomorphic to G psi. What this statement is saying is if I have two automorphisms and they differ by post-composition with an inner automorphism, so they're the same in the outer automorphism group, then their corresponding free-by-cyclic groups are the same. So the free-by-cyclic group really is a group associated to the outer class rather than the automorphism itself. So now group invariance. We're going to say property question mark of the outer automorphism group is a group invariant if G phi isomorphic to G psi implies phi has question mark if and only if psi has question mark. So it's kind of like the dynamical definition of being dynamical invariant, except I've replaced being dynamically equivalent with having the same group, free-by-cyclic group associated to them. So you pick phi and psi, and if for some miracle you have an isomorphism between those two free-by-cyclic group, then knowing something about a property of phi tells you something about a property of psi. So now we're talking about group invariance. And relatedly, I'll also put in here commensurability invariant. So this is option 2. And oh, should have used a different color. A commensurability invariant means if the two groups are not necessarily isomorphic, but commensurable, then you get the same implication. And being commensurable here means you can find there exist finite index subgroups H in G, H prime in G, G phi, and G psi, so that H is isomorphic to H prime. So they have finite index, isomorphic finite index subgroups. So the groups themselves might not be isomorphic, but up to finite index they are. So now I can ask about commensurability invariance of an automorphism, which is, why is this interesting? Secondary is over here. It's because I'm going to relate, if two automorphisms are dynamically equivalent, then they don't necessarily give you the same free-by-cyclic groups, the same mapping torus, but they're going to give you mapping tori that are isomorphic up to finite index. They're going to give you a commensurable mapping tori. So exercise, phi equivalent to psi, dynamically equivalent to psi implies G phi is commensurable. So isomorphic up to finite index. So it's a variation of this exercise here, but now you're sort of asking what happens when I pass to a power to the mapping torus. And yet, there exist examples. There are examples with phi not being dynamically equivalent to psi, and yet they still have commensurable free-by-cyclic subgroups. So there are examples that are not dynamically equivalent, but they give you isomorphic things. Similar to this, so you're really saying this implication is strict. You don't. There is no converse there. If you just because things are commensurable doesn't mean they're dynamically equivalent. In fact, it's actually worse. Like it fails in a very strong way, which is you can have phi being an automorphism of a rank 2 free group, and psi is an automorphism of a rank 5 free group. So they sort of live in different automorphism groups. So it doesn't even make sense to ask whether they're dynamically equivalent. And nevertheless, their free-by-cyclic groups are isomorphic or commensurable as abstract groups. So even like the rank of the free group that I used to define this automorphism is not a group invariant, is essentially the point there. Yeah, so non-example of a group invariant will be the rank. And now exercise, trying to think of the most economical way to do this. But I just want to say, being a finite order, toroidal, and the growth type, all those things are commensurability invariants. So there's things that are seen not just by the dynamics of the automorphism, but the group structure of the free-by-cyclic group. For the camera, for the people on Zoom, yeah, the new exercise is being finite order, toroidal, or growth type, which I haven't defined yet, all those things are commensurability invariants. So, and if you sort of think about this, it's something you can actually work out and write down and prove it yourself. So I think it's best to sort of do the exercise and think it through, because then you'll sort of see the types of arguments you want to make when you prove this naturally defined dynamical invariants are group invariants or geometric invariants or something like that. Okay, so that was the new exercise. And now for a theorem that is much recent. So towards the end of this mini course, you have seen a sketch of this theorem. So this is mine from a couple of years ago, very recent. And it says atoroidal plus irreducible. So this was one of the things that gave us Dowdall, Kapovich, Leininger proved that this property is a dynamical invariant. And I proved that it's actually a commensurability invariant. All right, so if you knew two automorphisms give you commensurable free-by-cyclic groups, then knowing that one of them is atoroidal and irreducible, it automatically tells you that the other one is too. So this was the hypothesis is a purely algebraic hypothesis, but then it allows you to sort of recover the dynamics of the automorphisms. Here's a question that seems like that's question with exclamation point, because it's ridiculous that, well, I don't know the answer to this. So if someone can answer it, I'll be very happy. Does there exist an example of a phi and a psi that are atoroidal and irreducible, but not commensurable? So yeah, and I'm not even requiring phi and psi to be automorphisms on the same group, on the same free group. So maybe like you're allowed to work with a free group of rank 5 here and a free group of rank 1 million if you want there. But can you come up with examples of a phi and psi that don't give you commensurable free-by-cyclic group? So it seems like an innocent question there, but what would you need to prove that something to these two things are not commensurable? You need a commensurable invariant that you can compute and show that it's different for phi and psi, right? So you need to come up with a new commensurable invariant that's able to distinguish those phi and psi. And as far as I know, there are none beyond just knowing being atoroidal and irreducible. But I'm assuming both of them are atoroidal and irreducible. So I need something else to distinguish them. And
volume.
Yes, invent volume. That's no, actually, I don't want to send you that way. Because let's say, for example, with, I didn't want to talk about this, but like hyperbolic 3 manifolds, you will say volume, but we don't even have examples of hyperbolic manifolds where we know that their volumes are not rationally related. So that's the thing you will need. So you want to some arithmetic invariant, whatever that means in this context, to tell them apart. But isn't that like the volume?
Yeah,
yeah, it's an open question. It's an open question. So that these terrible transcendental numbers, so showing that the ratio is not a rational number is really hard. Okay. So I might not get to geometry, but I do want to mention recent work by people in the room. All right. So I don't know. This is work by Sam Hughes and Monica Kudlinska. And it's a preprint from this year, and they prove a lot more, way other things, but I just want to mention something in the vein of what we have here, which is, oh, I have to tell you what the invariance we're interested in is here, which is a profinite invariance. So now, rather than talk about whether two groups are isomorphic or commensurable, you can ask whether they're profinitely isomorphic or. So the profinite completion of a group G is the inverse limit of G of finite quotients of G. So this inverse limit is with respect to finite index normal subgroups. So you can form this group, and this is the profinite completion. And then you can ask about something being a profinite invariant. So again, you have like property question mark, and you're going to say that G phi, and you look at it as profinite completion being isomorphic to G psi, and you look at its profinite completion, that implies phi has a question mark if and only if psi has question mark. And this hypothesis is slightly weaker than isomorphism because you can have groups that are not isomorphic. Well, in principle, you can have groups that are not isomorphic. Let's say even like residually finite groups that are not isomorphic but have isomorphic profinite completions. It's, I guess, an open problem whether that's true, whether such examples exist for free-by-cyclic groups, but yeah, so now you can talk about profinite invariance, which could be weaker than group invariance. And the theorem is that one of the things that they state in there is that being a toroidal is a profinite invariant. And I guess this was private communication. Being finite order should be. Yeah, so you won't say this in the preprint, but maybe it will show up in a next version or something. So being finite order and being toroidal, we know those are group invariants, commensurability invariants, but you can sort of ask a completely different question, whether they're profinite invariants. And as far as I know, there's nothing known about profinite invariance other than this statement in general. And they ask about irreducibility. So question, irreducible, is that a profinite invariance? Under some hypothesis there, yeah, it's unclear even if you make very strong hypothesis whether you can get invariance there. All right, so that was the profinite stuff that I wanted to talk about.
We have examples of free-by-cyclic groups that are not isomorphic but have the same profinite that we can, or we don't.
I think it's open whether free-by-cyclic groups are profinitely rigid. So yeah, I will say I do not know much about profinite things, but they will be the great people to ask about this.
3 weeks will be a lot of people.
Yeah. All right. So again, this is like current work. So if you any of these dynamical invariants, you can ask whether it's a profinite invariance, and that's an open question, basically. So I promised lots of open questions to take home. There you have it. All right, and now let's go to geometry in the last 5 minutes. to geometry. So we had our G phi, our free-by-cyclic group, and we know it's generated just by the fact that we have a presentation that has these generators by the finite set A1 to AR and T. And we can consider the Cayley graph, gamma sub S, which is the Cayley graph of G phi with respect to that finite generating set. And just for concreteness, I'll say vertices are elements of G phi. And edges are going to be, you have an edge between G1 and G2, or G and G prime, if there exists an element, what? If G inverse G prime is an element of S. Okay, so here's we have a graph. It's connected because the group is generated by S. And then you can consider the group action on the Cayley graph by left multiplication. So an element H acts by just adding an H here and an H here, and that's going to be a group action. And if you identify the edges of your graph with the unit interval 0, 1, then you've sort of, you can turn this Cayley graph into a matrix space, right? And the group is going to be acting by isometries on this matrix space. So I'll say by isometries. When I write isom of an action, there's an implied metric here, and it's acting by isometry. All right, so I'll define a quasi-isometry and then state Milnor-Schwarz lemma, and that will be the end. So quasi-isometries. I have two metric spaces, X with a metric D, and Y with a metric delta, and a function I from one to the other. And it's going to be a QY embedding. If you have some constant K, multiplicative constants of greater than or equal to 1, additive constant 0, greater than or equal to 0. And let's see, an isometry or an isometric embedding will keep the distances the same. So delta of the image of P and Q will equal the original distance between P and Q. But then we're dealing with, let's say we want something that's not exactly an isometry, but almost an isometry. So you can make it by Lipschitz by adding a multiplicative constant over here, and then divide by that same constant on the other side. And then you add an additive error fudge factor, and you subtract it on the other side. And that's going to be, so it's a coarsely by Lipschitz map. And then it's also coarsely surjective for it to be a quasi-isometry, coarsely surjective. So there exists some uniform constant D greater than or equal to 0, and Y is contained in the D neighborhood of the image. And okay, this is Milnor-Schwarz, but it's much more general than this, but I've run out of time. So I'll say any two Cayley graphs of a finitely generated group are quasi-isometric. So in particular, you can, if you want to define things, properties and you know that that property is a QI invariant, then you can just say the group has this property if its Cayley graph has that property, right? So delta hyperbolicity is something like you can define in terms of the Cayley graph. But more generally, you can sort of deal with geometric models that don't have to be Cayley graphs if you have a better model to work with. And so QI invariant for us will say that property question mark is a QI invariant if G phi being quasi-isometric to G psi implies phi has question mark if and only if psi has question mark. Yeah. And so the last thing that I sort of want to give here is a theorem of lots of people. I'll give more details later, but being finite order is a QI invariant. And then a theorem of Brinkman, which I gave at the very beginning, is that being heteroidal is a QI invariant. But in general, it's really hard to find QI invariants. And I'll stop there for today.
Questions for JP? Is irreducible heteroidal QI invariant?
That's my favorite open question right now. So question is heteroidal and irreducible a QI invariant? Well, we know it's a commensurability, so that's a start. But it's a long way between finite index to QI. Yes.
Yeah. The Milner-Schwartz theorem aims to get out so finite integration group are obviously isomorphic, but quasi-isometric. Does that work for a finite generating set?
Yeah. No. So I'm working under the assumption that my Cayley graphs are with respect to finite sets, finite generating sets. So Cayley graphs or finitely generated groups with respect to a finite generating set. Finite generating set. Thanks for the clarification.
There's a point where you said that there were dynamically different homeomorphisms that are the same free-by-cyclic, and then you get rid of them where they have different maps.
I didn't explicitly write one, but I said they do exist, yeah. Yeah, that's not the only reason why. If they're in the same rank, yeah, you can sort of look at like it'll come up later, but like growth types. So if they're exponentially growing, and then you can show like their exponential growth rates are not rationally related or something in some way, then yeah.
Okay, let's thank JP again.